Good afternoon to one and all to here. On behalf of National Engineering College, Kovilpatti, I welcome you all. This webinar series from our department, Science and Humanities, conducting every month join with the New Year with this second webinar.
Dr. Saha Omar. She completed her PhD in University of Malaya 2015 to 18, and then later she joined postdoctoral fellow there. After that, she went to University Kebangswan, Malaysia. Till now, she is continuing her research and the recruitment process. Her area of interest includes electrochemical energy storage devices, especially supercapacitor and photocatalysis. Till now, her citation goes up to 2000, and currently she is supervising 6 research scholars, and she received 2 funded projects, and she also acts as a reviewer for 3 journals, including Ceramics International, Journal of Energy Storage, Electroanalytical Chemistry. She published a more number of papers in international reputed journals. So now the floor is open for ma'am. And now we are listening her words. We are waiting to listen her words about supercapacitor. So thank you, ma'am. Thank you so much, ma'am, for accepting our invitation. And we all are waiting for your talk on supercapacitor. Now the session, I hand over the session to ma'am.
Thank you. May I share the slide? Can you see my slide?
Yeah, yes, ma'am.
Okay. Good evening. Good afternoon and good evening. Right now in Malaysia, it is 5:30. Okay, and first of all, I will Department of and inviting talk in this webinar, and a little bit introduction about electrochemical energy storage or EES, and then go to trace and supercapacitors, because these devices are chemical energy storage, and I will explain the difference in terms of the designs, working principles, and the selection of materials. And then supercapacitor also will explain its design, working principle, and some of my research works. Okay, so I'm from the Department of Applied Physics, Science and Technology, University Kebangswan Malaysia, or UKM. English is named as the National University of Malaysia. And our university is located about 55 kilometers from our Kuala Lumpur. And okay, so the introduction about electrochemical energy storage.
நான் லேப்டாப்ல வச்சு தான் கேட்டுட்டு இருக்கேன். எனக்கு கேட்கல.
Energy is important.
அது அவங்க வாய்ஸ் கம்மியா மெதுவா பேசுறாங்க.
In our daily life. So then but we depend too much on the fossil fuels, and the effect is that we are now facing global warming issues. So most of the countries agree to try to the average global warming 1.5 degrees C. One of the approach that all of us are taking now is okay. And what was okay? So some of the countries depends on hydropower, other countries depend on the nuclear reactor. Rock and also liquid of the earth to keep the heat. And nuclear power, we have a large tank filled with the motor to keep the heat. So we have many types of energy storage, and the one that I'm going to present now is the electrode, and the electrodes are separated by a membrane separator. So the function of separator is just to avoid the short circuit. To install the off-grid solar panel at home also, you can use batteries, especially the batteries, and then also this can be used in the vehicle and to this applications like consumer electronics we use in our laptops, in our handphones. Okay. Okay. First, I will start lithium-ion batteries. For batteries, I'll focus on lithium-ion batteries or LIB because LIB represents about 90% of the battery systems. So basically, LIB rely on lithium ions for energy by creating electric potential difference between anode and cathode. And actually, LIB, there are different types. They use lithium-based electrolyte, but they have different names based on the material that they use as the anode. So they have lithium iron phosphate battery, lithium cobalt oxide battery, lithium nickel manganese battery, and so on. But these lithium ion batteries have their own pros and cons. For example, like lithium cobalt. Okay, lithium cobalt oxide might have, they have the high specific energy, uh, go performance.
Muted.
It has specific energy. However, its lifespan is a bit lower and it is not very. And also, for example, like lithium manganese oxide. This device don't is not really good in terms of its lifespan. So, but for other factors, quite. And for LFP, lithium ferrum phosphate, it has many layers. And for cathode, LID, it is coated typically. Okay, for example, this one is lithium cobalt, lithium ion cobalt. So for this cathode, it is coated with lithium cobalt oxide. And this lithium cobalt oxide meaning that the cobalt oxide is doped with lithium ion. So during happen is if we connect this device to the power supply, so the positive is how we got the current flow, and anode will flow back towards the cathode. And at the same time, the lithium ion will be back to the cathode and receive the electrons and then stay at the cathode. Okay, then next, supercapacitors. Supercapacitors, so like batteries, they exist in different sizes. And how does it work? Okay, like batteries, okay, they have two electrodes, but this time they are arranged in symmetrical order. So, for example, like this one, this electrode and this electrode, we don't call it as the anode and cathode. We call it positive electrode and negative electrode based on which side of the power supply that we connect to. Okay, so the carbon, this represents the carbon-based material that we usually use to prepare the of supercapacitors. The red circle represent the negative ions of electrolyte, and the yellow circle represent the positive ion of electrolyte. So without the external circuit. Okay, and the movement of the electrolyte ions from the center towards the oppositely charged of electrode will happen until all of the positive ions and ions are separated. So at this stage, we can say that the supercapacitor is can be charged and deliver energy, and energy density means how much energy can be stored by the device. So we can see the LIB, lithium-ion battery, is positioned here. It has higher energy density than supercapacitor, but lower power density than supercapacitor. So it means that LIB so higher energy than supercapacitors, but it takes time to be fully charged. While for capacitor, has higher power density than LIB, but lower energy density. So it means that even though they can be charged and discharged, but they are unable to store large amount of energy. So why there is a gap, there is a huge gap between the batteries, LIB, and also supercapacitors. So the difference, the distinction that we can see, that we saw from the Rigoni plots, is because of the types of electrodes that we devise. Okay, before we go to the electrode, I'll brief introduce about the model of the structure of electrified interfaces. So there are actually three different models that trying to explain what happened when the electrolyte ions interact with the electrode surface. So the first model is called as Helmholtz model. So for Helmholtz model, models stated that when the electrolyte ion interact with the electrode surface, there will be like tightly bound of the electrolyte ions on the surface of the electrode surface, on the surface of the electrode is moving. So the first model cannot be used to explain the interaction between the electrolyte ions and electrode. They since through their they stated at higher concentration of electrolyte, we tend to very high capacitance, infinite capacitance, which is also not correct. Okay, and then there is the third model, and for Stern model, he called the model Helmholtz model and also Guichard models. So three models. The third model is the most suitable to explain the interaction between the electrolyte ions and electrode. So from that structure, we come up with different names of electrode. We have capacitive electrode, pseudo-capacitive electrode, and battery type electrode. So what is capacitive electrode? So capacitive electrode is usually we use in capacitors. Basically, capacitive electrode use carbon material as material. Let's say, for example, in this figure, the electrode is negatively charged, so it will attract the positive ions of the electrolytes. So the red circle is positive ion, so the positive ion will be absorbed onto the surface of capacitive electrode. So this process is called as electrostatic or ion adsorption, and also can be called as the physical interaction. Okay? And next is pseudo-capacitive electrode. What happened is some material, they only allows the ion adsorption on the surface of the electrode material, but some material, the electrolyte ions can between the crystal layers of the materials, and when the integration happen, it will be like redox reaction happen only on the surface. Okay, and third electrode, which is the battery electrode, there will be a diffusion of electrolyte ions between the crystal structure. But the difference between the battery type electrode and pseudo-capacitive electrode is that the redox reaction or Faraday reaction at pseudo-capacitive electrode is faster as compared to the battery type electrode. So the redox reaction happen at the battery type electrode is slower. Capacitors and more. Okay, and so below figure capacitive electrode and pseudo-capacitive electrode. All of the capacitive electrode and some of the pseudo-capacitive electrode is governed by surface control kinetics, and the pseudo-capacitive electrode and all of the battery type electrodes is governed by the diffusion control kinetics. Okay, so once the electrolyte ions diffuse throughout the crystal structure of the electrode, so we call it as the diffusion. This image different square shape, okay, which means that the electrostatic reaction happen at the electrode, no chemical reaction. The pseudo-capacitive electrode, it tries to mimic the shape of the CV of capacitive electrode, but if you look closely, there are peaks of oxidation and reduction. Okay, oxidation at the anodic part and reduction cathode part. So it means there is redox reaction happen at the surface. So the redox reaction is fast. So that's why the peak is quite broad. And like I said previously, some of the electrode also offers the intercalation for the electrolyte ions we also curve like this. Some part is a bit square, but some part is narrower. So it means that the integration happen. But different with battery type electrode. There are peaks at the anodic and cathodic. The peaks intense, so we can clearly see the difference between the peaks at the pseudo capacitive electrode, which is broad, and intense peak at the battery type electrode. So they reported that they got pseudo capacitive electrode, even though got this type of CV profile, but actually it is wrong. It is battery type electrode. So it is important for us to recognize the types of electrodes, because if we don't understand, we should use capacity, not capacitance. And then this is the discharge curve, okay, CV, and for the electrode and pseudo capacitive electrode, no phase change is happen, okay, during charging and discharging, while for the battery electrode, there is a phase change, okay, during the repetitive charging and discharging. And this is IV, means that it represents the response of current over the scan rate. So we can the graph, and then we can find the gradients. So if the gradient is approximately 1, so it means that it is capacitive electrode or pseudo capacitive electrode. But if the gradient is 0.5, it's control. While if the gradient is 0.5, it means that the governed by diffusion. And below is the example of the material for each of the electrodes. Like capacitive electrode, basically, typically they use TNT, activated carbon, graphene. Okay? And for pseudo-capacitive electrode, for surface redox, use ruthenium oxide, manganese oxide, titanium carbide. And for the intercalation, non-lithium pentoxide. Okay, so it means that for pseudo-capacitive electrode really depends on the material of the substrate and the material of the material coated onto the substrate. Okay, then battery type electrode, previously shown, lithium carbide oxide, lithium ferrum phosphate, and so on. The supercapacitors. Supercapacitors use capacity utilize the combination of electrostatic and redox battery type electrode in during charging and discharging. So how supercapacitor works? Okay, before charging, it is neutral. Okay, no movement of the ions until we connect the supercapacitor to the power supply. So the electrode with the carbon-based material negative, and the electrode coated with the so because of there is oxidation, reaction happen when the negative ion of electrolyte interact with the positive electrode. So until all of the electrolyte ions are separated. And during discharging, the electrolyte ions will leave the electrode, and then will be back to the bulk electrolytes. And what happened during that time is the battery electrode will go through reduction process. So the material will receive back the electron. And at the same time, the negative electrode will go through electrostatic reaction. Okay, so for the material selection, there are 6 general factors that people usually consider. First is cost. Some people, they don't mind about the cost as long as the material is. Of course, when we want to produce material energy storage, we really concern the capability of the material to store a lot of energy and to be charged faster. And fourth is the cycle life. Of course, we want high stability of the electrode materials. Otherwise, if the material is not stable, it can impact the stability of the device. And fifth and sixth is safety. Okay? If possible, we want the material to be safe, not flammable. Okay? And microscopically, we want the material to be very stable during the repetitive short diffusion channels for the movement of the electrolyte ions, because the short diffusion channels for the electrolyte ions can influence the rate capability of the electrode. So rate capability means the ability of the electrode to maintain its capacitance from low current applied to the higher current applied. And these are the strategies to improve the performance of the electrode. So typically when we use only one set of material, the material either they can offer high specific capacity or high rate capability. Composite the metal oxide with carbon-based material to fasten the electronic conduction of the materials. And these are the most famous carbon-based material. We have activated carbon, carbon nanotube, and the similarities that we can see from these two images, they have a lot of pores. Okay? And this is graphene. Graphene doesn't have many pores, but it offers a large surface area. This is graphene. Cobalt oxide nanocube by compositing the nanocube with graphene. So this translucent shade is the transparent RG is right, and the dots is the cobalt oxide. So this image shows that the cobalt oxide anchored on the shade of RgO. So after we composite the cobalt oxide with RgO, we notice that there is enhancement in the electrochemical performance. So this is the reference. And second is metallic doping. We can also tune the band gap or modify the intrinsic property of the material by doping metal with another metal. So in the morphology. But if there's a change in morphology, it means that the doping process is success. Okay? And among these electrodes, doped with manganese shows the highest performance. And third, we can also introduce heterointerface, diffusible channels, increase the specific surface area. Okay, and for diffusible channels, it means that we can create pores in the electrode materials. So what we did in this work is we composite the amorphous structure of nickel phosphate and crystalline structure of silver phosphate. So this big particle is the nickel phosphate. This, if you see closely, this particle has a lot of pores. Okay, and this is the close-up view. Nickel phosphate has lattice fringe, so it means that silver phosphate has crystalline structure, while for nickel phosphate doesn't have any lattice fringe. So it means that nickel phosphate has amorphous structure. So like I said previously, if the material has a lot of pores, it means that they can provide more channels for the diffusion of electrolyte ions. And then we can also introduce the edge active sites. Either we can, for example, like we can reduce the size of the particles from bulk to nano size. Okay? And this is the example. This is our recent paper where we synthesize nickel silicide binder-free electrode through CVD method. So in this, the first figure, the first episode image shows the two layers. The first layer is and the second layer is the nickel silicide nanowire. Okay, and this is the periodic table that shows at least elements are suitable for batteries. And for the gray, if the electronegativity difference is low, so the material tend to form the atoms tend to bind through the covalent bonds. So the material tend to have band structure. Okay, so this is the example. And if the electronegativity is high, so we tend to get if the electronegativity is low, we tend to get covalent bound. But if the electronegativity difference is high, we tend to get ionic bound. So the ionic and also covalent bound, it tend to make the material to form either dense structure or polypack structure. So this is example of the dense structure of the materials, and these are the examples of the polypack structures. So actually, the dense structure of the material is not very good for the energy storage because there is no space for the diffusion of the electrolyte ions. But if the structure has a gap between the layers, so it means that they will allow the electrolyte ions to passing through them. So there's a gap. So this is the electrolyte ions. So the electron is able to go passing the crystal structure of the materials, and this is the pack structures, another form of structures. So there's a huge gap between the crystal lattice. So the electrolyte ions able passing through and interact throughout the electrode throughout the structure of the electrode material. So the larger the gap between the crystal, more spaces for the electrolyte ion to passing through. So different lattice, different crystal structure can impact the electrochemical performance. So for spine, okay, you can the curve for the discharge curve for the spinal is tend to be like this, and this one tend to be like this, longer. So we can see different shapes or different profile of the discharge curve for different structure of the ions. And this is another they varied the crystal structure of the electrode materials, and they use different types of electrolyte ions. So here we have lithium, sodium, and potassium. And lithium has the smallest electrolyte. No, it has the smallest ionic radius, okay, which is 0.76 angstrom. And sodium larger than lithium, and potassium larger than is the largest. Okay, its ionic radius is around 1.3 angstrom. So what this figure trying to show us is that, for example, like crystalline structure, the first, so all of because of the gap is around 2.65 angstrom. So they all of the electrolyte can all types of electrolyte ions can penetrate to the crystal structure. They're able to diffuse throughout the crystal structure. And for the spinal structure, this sample can only allow lithium, okay, because the gap is larger than lithium. But for other types of electrolyte ions, they cannot pass through easily. Okay, and then for this structure also, they have different structure. It means that the gap structure will be also different. So this structure allow lithium, but other types of electron ions can between the atoms is large, and another part of the and some part is large and another part is small. So we
டியூட்டரை போய் பார்த்துட்டு வாங்க அப்படின்ட்டு
we coat the electrode
எதுக்காக
material onto the
சொன்னாங்கன்னு சொல்லுங்க.
substrate by using binder. So binder we use PVDF usually.
எதுக்காக சொன்னாங்கம்மா, நீங்க ஏதாச்சும் பேசுனீங்களா?
And the second method is we
சொல்லுங்க தம்பி.
directly grow particles onto the substrate.
நீங்க எதுமே சொல்லாம அவங்க வந்து செல்ல மாட்டாங்க.
So for the first step is there is advantage for the first step where if we use polymer binder, binder, the advantage is we don't really have to concern about the of the electrode, and also the total activity is no longer because of the polymer binder, but it's because of electrode material. And this is the bare substrate, and this is the substrate coated with the material. And the coated part is can be immersed inside the electrode set up for the electrochemical analysis. So usually when we prepare the electrode, we can test the performance of the electrode using 3 electrode setup. Yeah. So this is our electrode, and another 2 electrode is the standard electrode. We use platinum wire and also reference electrode. So for reference electrode, we can either use silver chloride or SCE or mercury oxide. And this is the potentiostat that we use. In our lab, we have auto lab potentiostats. So this setup, these 3 electrode setup is connected to the stack, and the data can be viewed using monitor. And for testing, there are three basic techniques can we use. First is cyclic voltammetry, CV. Second is galvanostatic charge discharge, GCD. And third is electrochemical impedance spectroscopy. So basically, we can calculate the specific capacity using cyclic voltammetry, CV, and GCD. For EIS, is used to determine the conductivity or the internal resistance when there is interaction between the electrode and electrolyte ion. Okay, this is the example of the electrochemical studies. For figure A, okay, in this work, what we did is we prepared 4 different materials. First is polyaniline, second is nickel phosphate, which is amorphous nickel phosphate, and third is nickel phosphate composited with silver phosphate, and third and fourth is the composite of polyaniline, amorphous structure of nickel phosphate, and crystalline structure of phosphate. So in this CV, we can look at the area under the curve. Okay, so in this figure, the polyaniline nickel phosphate silver phosphate has the largest CV area. So it means that it has the highest specific capacity, but it depends on the weight of the active materials. So in this case, after we take into account the mass of the material and then we calculate the specific capacity, so the polyaniline nickel phosphate silver phosphate really has the highest specific capacity. And what we can interpret from this figure besides, so it means that diffusion process is happening during the charging at the anodic and discharging at the cathodic. And for figure B is also CV curve, but the parameter in CV is the scan rate. So the highest the scan rate that we use, the faster the electrode to charging and discharging. Yeah. And figure C is the GCD curve. So from here to here is charging, and from the limit is around 0.45, and from 0.45 to 0 it is discharging. So from here we can calculate the capacity through the discharge durations. So if we compare the discharge duration among these electrodes, polyaniline nickel phosphate silver phosphate has the longest discharge curve. It means that it can deliver us energy longer as compared to other electrodes. And figure D is the GCD, where we varied the current density from 1 to 8 ampere per gram for all electrodes. So this is only the curve for one electrode, and we have to run for another 3 electrodes. So from GCD curve, we can calculate the specific capacity and plot this graph. So from here, we can see clearly which sample has the highest specific capacity. So in this figure, polyaniline nickel phosphate silver phosphate has the highest specific capacity. But one thing I want to highlight in this graph is that for nickel phosphate at the lowest current density, it has higher specific capacity, but the specific high specificity than nickel phosphate, which is the red curve. But it only happened at the lower current density. But with increased density, specific capacity started to drop. While for the nickel phosphate, silver phosphate, it able to maintain the specific capacity from one of the lowest current density to the highest current density. So in this figure, nickel phosphate, silver phosphate has the highest rate capacity as other electrodes. So why this happened? It's because of the influence of structure. So before I explain what happened actually, I will also present the next plot. Okay, and we can focus here. This figure B is also the same image of figure. We just close up the V plot. So what we can look at this curve is our equivalent series resistance. The polyaniline nickel phosphate silver phosphate electrode has the lowest ESR value. Okay, it means that it has the highest internal conductivity as compared to other electrode. And second is, and look at the circle, has the largest semicircle, has the highest diffusion for the electrolyte ions. And then we can also at the slope of the curve. If the slope is almost vertical, it means it has the capacity property. Okay, so to explain, the nickel phosphate has a lot of, okay, at the lower current applied, all the pores can be accessed by the electron ions. This would not if apply higher current. At the higher current applied, the not all of the area can be accessed by the electrolyte. And in contrast, for silver phosphate has crystalline structure. It has structure. So the area that are available for reaction with electrolyte ions is as compared to nickel phosphate. So because of this structure, it will not have problem with the number of accessible area for the diffusion of electrolyte ions. And another factor is that nickel phosphate has conductivity as compared to the silver phosphate. So without silver phosphate, the electron that are to the nickel phosphate is slow because of which is has conductivity. But with the addition of silver phosphate, actually can shorten the path for the movement of electron. Okay? And the green one is polyaniline. Okay? It's just used to further enhance the performance. But still, the rate capability of polyaniline nickel phosphate silver phosphate is lower to the nickel phosphate silver phosphate, which is it has 73% for nickel phosphate silver phosphate 76%. Also, this also can strongly support stability is influenced by the structure because polyaniline has the semi-crystalline structure. Okay, after we tested the performance of a single electrode, fabricate the device. So before we fabricate, can check CB profile of the capacitor electrode and the electrode. So in this, we use activated carbon as the of the capacitive electrode is nickel phosphate. Okay, so if you look at capacitive electrode has a potential window of 1 volt, and the battery type electrode has the potential window of 0.6 volt. So when we to add up voltage of the potential difference of the capacitive electrode and battery type, we expect that the potential window of the device is also around 1.6 volt. So after combine the to a device, we try to check the CB profile at various potential window. So this one from 0 to 0.4, this one from 0 to 1.2, 0 to 1.4, 0 to 1.6. Okay, and this curve, okay, this is the CV curve of the device. So it's still, you can see that the curve is still there's no decomposition of what happened at this potential window range. Okay? So it is agree agree with the potential difference or the potential window that we sum up from the capacitive electrode and the electrode. And this profile of the device when we vary the scan rate from lower carried to the, and this is the GCD curve of the device. So this is charging and this is discharging. So again, like testing, from GCD we can calculate the specific capacity. We can determine the energy density and power density. Also, this is wrongly labeled. But the device which consists of polyaniline nickel phosphate silver phosphate has the stability as compared to other electrodes. Okay, so that's all from the slides. I would like to thanks to the Department of Applied Physics, Faculty of Science and Technology, University Kebangsaan Malaysia, for giving me a chance to continue with my research. And not to forget the Department of Physics, Faculty of Science, University of Malaya, where University of Malaya is where I did my PhD. So thank you. I think that's all from me. Thank you.
Thank you, ma'am. Dear participants, now the session is open for. If you have any questions, you may ask with our professor, or you may send your question through chat box.
The going supplement, madam.
Sir, can you repeat the question?
Ma'am, you said that the going supplement model is applicable only at lower concentrations, right? Lower concentrations of electrolyte. Why it's so?
Because of this is because of the equation that they derive through the equation. When they use a higher current or higher concentration of the electrolyte ions, what happened is through the formulation, the diffusion is said that we tend to get very high specific capacity if we use higher current, higher concentration of electrolyte ions. So that is actually not true for the interaction of electrolyte and electrodes, because it is impossible for us to get infinity capacitance if we use higher concentration of electrolyte. Theoretically, yes, because supercapacitors don't store energy through the reaction. So basically, electrostatic reaction is very reaction. So because of supercapacitors don't store energy through the redox reaction, so it will not have problem of low stability or poor ability to store energy from lower current applied to the higher current applied. So yes, supercapacitors can handle high current, really. But still it depends on how you prepare the materials. If your materials is good enough, it is very conductive, it has higher surface area, so it's supposed to be able to handle high current. Operating voltage of supercapacitors also depends on how you prepare the material, how you assemble the device. But the commercialized supercapacitors, they get 3 volt of potential window. So it depends on the materials. So if you one single device, you can get very high potential window. What you can do is either you can enlight of the electrode, or you can connect more than one, conduct the experiment using 1 ampere. But some potential stat, the potential stat is not able to conduct experiment at high current.
Ma'am, in your one of the slides regarding the metal doping, in your present work, you stated that from the semi-majors, the morphology changes shows the metal is doped into the material, and it is not a composite. Because if it is composite, then there won't be any morphology change. That's why so, ma'am. Why for a composite material, why the morphology won't change?
Actually, the initial morphology won't change. For example, like if you mix material A as, okay, for example, like material A has a cube structure morphology, and for the material B has a sphere morphology. For composite, if you mix cube with sphere, there will be no changes in morphology. But what you can see from the morphology is that the circle will just attach to the cube. So that is for composite. They will not change in the lattice structure of the material, because the materials just combine physically. For the hybrid, okay, for the doping is example of hybrid. The doping, if for example, like just now in the work, we dope manganese into the cobalt sulfides. So the manganese ion will diffuse will put themselves into the cobalt lattice structure. So when there is a change in the lattice structure, of course, this can also affect the structure of the crystal lattice and also the morphology of the materials. So there are two different composition. First is composite, where the materials are just physically attached, and hybrid, although the ions is infused into the crystal lattice of the host materials.
Hello, ma'am. Good evening,
Hi,
ma'am.
evening.
Uh, Ma'am, I just wanted to ask you about the preparation of the electrode. Basically, when we coat the first method, actually, I'm also working on it right now. So when we coat on that nickel foam, is it compulsory that we have to quote a minimum amount? That is like in some of the papers they've mentioned somewhere around 2 mg they've quoted. But practically, is it possible or how is it, ma'am? Because then only we'll be able to find that GCD 1 ampere per gram, and accordingly we are able to calculate the current, and we are able to do the next step. So how is it, ma'am? The coating is very important. So how, could you give us some tips related to it? It would be helpful.
Okay, thank you for the question. So, of the active material is very important because, if possible, we want to get the lightest light materials, because from the mass we can influence the total specific capacity of electrodes. So if your sample is in form and you want to fabricate into electrode, you have to mix with polymer binder. Yes, you can use very tiny amount of active material, but when you use very small amount of them to make sure the substrate is uniformly coated with the active materials. So if the nickel coated free electrodes, so you don't really have to worry about the uniformity coating of the electrode materials onto the substrate. So yes, you can use the very light amount of active material, but you have to consider after you mix polymer binder, the slurry is smooth and enough to coat onto the of the electrode surface of the substrate. I hope that answering your question.
Yes, ma'am. Thank you so much, ma'am.
To use good to getting good capacity.
Also, it depends on the activity, but if you are interested in flexible devices in the current work, uh, can offers porous structure. Okay, it can offers higher surface for the difference of the electrode material, and but it doesn't mean that you use nickel foam you will get very good performance of the device. So it's still, if let's say you use lower conductivity of substrate, but the coating is uniform, and if your material is good, has good conductivity, good capacity, still it can offer high specific capacity of the device. So substrate is abstract, okay? It's subjective. The most important is how well your is and how well the contact area between the material and the and electrolyte types. So if you use organic electrolyte, you tend larger voltage of the device than if you use aqueous electrolytes.
எந்த ஸ்கூல் போறீங்க கோபியா மேம்?
Thank you so much, ma'am. Ramasub sir. Ramasub sir.
Question on supercapacitor. On the behalf of museum management, we are feel happy to receive such a response from research scholar side. Yes, absolutely, we are very happy. And first of all, I would like to thank the management, sir, Dean R&D, Professor M. Nilakaman sir, for giving this wonderful opportunity for organizing such a series. So I thank you all. And next one, I wish to thank Fatin ma'am when I asked her readily accept the invitation and she prepared a nice session for us. Thank you so much, ma'am. I hope we will continue the collaboration also. Thank you so much, ma'am. And
Thank you for inviting.
next to the participants, uh, the participants all we thank you. We thank you so much for your wonderful responses. We are extremely next one. I want to thank my colleagues also who supports throughout the webinar for arrangement such to arrange this one wonderful thing. Thank you so much.
சரி
Dear
ஓகே
participants, thank you so much.